Can a human being survive falling from space? It's a question that sounds like pure science fiction, but let's take it seriously for a moment. Imagine you're floating at the edge of the world, hundreds of thousands of feet above Earth, staring down at the clouds and oceans far, far below. Then something goes wrong. A malfunction, a wrong step, and suddenly, you're falling. No spaceship, no parachute. Just you plummeting toward Earth. Is there any way you could survive? To answer this, we need to understand what falling from space actually means. Space doesn't have a hard edge. It's not like 1 second you're in Earth's atmosphere and the next second you're in the vacuum of the cosmos. Instead, the atmosphere thins gradually as you go higher. But internationally, the beginning of space is defined as the Kármán line, located 100 kilometers or 62 miles above sea level. That's the boundary where aircraft can no longer generate lift through normal aerodynamics, and where space truly begins. So let's suppose you're falling from that point, 100 kilometers up. It's incredibly high, but it's not orbital height. To put it in perspective, the International Space Station orbits at about 400 kilometers up, 4 times higher, and it's moving sideways at a blazing 28,000 kilometers per hour. From that height and speed, you wouldn't just fall straight down. You'd re-enter Earth's atmosphere at hypersonic velocity, and without a protective heat shield, you'd burn up from the friction and compression of air molecules in a matter of seconds. There's simply no surviving a fall from orbit without a specialized re-entry system. But from the edge of space, from the Kármán line, things are different. You're still falling through the atmosphere, albeit starting in the thinnest possible layer. The air is too thin to breathe, and there's almost no resistance at first. But crucially, you're not moving sideways at orbital speed. You're just dropping straight down. That changes everything. The first thing you'd have to worry about is exposure to vacuum. Space is an airless void. If you're not wearing a pressurized suit, your body is in big trouble, immediately. Within 15 seconds, you'd lose consciousness due to lack of oxygen. Your saliva would begin to boil due to the low pressure. Your skin would swell, but contrary to what you see in the movies, you wouldn't explode. If you're rescued quickly enough, it's actually possible to survive brief exposure to vacuum. But beyond 90 seconds or so, brain damage and death become almost inevitable. So, step 1 in our survival scenario, you need a full-body pressure suit, not just a warm jacket or oxygen mask. You need a sealed, pressurized system that provides oxygen, regulates temperature, and protects your body from the effects of space. Think NASA's EVA suits, or the custom suit worn by Felix Baumgartner in 2012. Now, let's talk about speed. Once you begin falling, gravity pulls you downward at 9.8 meters per second squared. At first, you accelerate rapidly, but there's a twist. You're not in a vacuum forever. The lower you fall, the denser the air becomes. That air pushes back against your body, slowing you down. This creates a phenomenon known as terminal velocity, the maximum speed you can fall through the air. In normal skydiving, terminal velocity is around 200 kilometers per hour, or 125 miles per hour. But from the edge of space, it's a completely different story. There's so little resistance up there that you accelerate far beyond the speed of sound. In fact, Baumgartner himself reached speeds of over 1,300 kilometers per hour, more than Mach 1.2, during his fall from 39 kilometers up. If you were falling from 100 kilometers, your top speed would be even higher, possibly approaching Mach 2 before drag slows you down. Now here's where survival gets really interesting, because even though you're going incredibly fast, the heat generated by your fall isn't enough to kill you. Why? Because the heating astronauts experience during re-entry comes mostly from traveling at orbital speeds, not just from falling. You're not moving at 28,000 kilometers per hour. You're falling straight down, not sideways. That difference is life or death. As you pass through 70, 60, and 50 kilometers in altitude, the atmosphere thickens dramatically. The air molecules increase, drag intensifies, and your body starts to decelerate. If you're wearing a high-altitude suit that can handle the pressure differential and heat buildup, your body will survive this part, although it will be one of the most extreme and violent experiences a human could go through. Eventually, at around 5 kilometers above sea level, conditions become similar to those of a standard skydive. At that point, assuming you're conscious and your systems are intact, you deploy a parachute. That parachute would slow you to a gentle descent, and believe it or not, you could land safely. So what does all this mean? Can you survive a fall from space? The final answer is yes, but only under very specific conditions. You need a pressurized suit to keep your body functional in vacuum. You need a thermal layer to survive high-speed descent. You need a parachute system to slow you down at the right time. And most importantly, you need to start your fall from a suborbital height, like 100 kilometers or less. If you're falling from actual orbit, your chances are effectively zero without a re-entry capsule or some kind of heat shield technology. This kind of fall has already been tested. In 2014, Google executive Alan Eustace broke the world record for high-altitude freefall by jumping from 41.4 kilometers. That's still below the Comm line, but only by a bit. He survived. He reached supersonic speed, and he returned safely. Someday, someone may attempt to jump from 100 kilometers, or even higher. With the right technology, it might just be possible.